Okay, recording's re-rolling. It's Monday, November 1st. You guys all just turned in your energy quiz, so I'll get those graded pretty soon. Let's look at next few assignments coming up. So you guys have an AP classroom multiple choice questions. This is Unit 5. Let's have that due 1 week from now. Next week, by the way, is going to be kind of a weird week for a couple of reasons. Next Tuesday, there's some standardized tests that I have to go proctor, so that'll be day. And then you guys might know next Thursday is Veterans Day. So yeah, next week's going to be kind of choppy. I guess we'll deal with that when we get there, but that's coming up. Then I have new pages for you guys. So clipped to the front of your desk are 2 pages. One looks like this, says chapter 6. Chapter 6. Okay. Here's your main homework problems from chapter 6 and also a bonus homework. Last couple of bonus homeworks I've been doing 20 out of 10. I'm going to switch that to 20 out of 20, so there'll still be a bonus option. It'll still boost your grade a little bit, but it's just going to be out of 20 points. Okay. There's another page also clipped to the front of your desk that you want that looks like this. It has a bunch of boxes on it, some formulas at the top. And this page I'm going to refer to as I go through the notes and tell you guys the story of momentum. Momentum is what we're looking at. It's also chapter 6 in your book, momentum. All right, you guys ready to learn all about momentum? Yeah, do this. We're eventually going to answer that baseball question, but probably not until like first thing tomorrow. That's about where I've been getting in the notes today. So momentum. I'm going to designate this with a lowercase p. I'll even put an arrow above that. I think I mentioned this before, but do you guys remember if there's a letter, or sorry, if there's an arrow hovering above a letter, what does that arrow mean? It's what kind of variable?
Vector.
Yeah, vector. Yeah. So it's a vector quantity. Okay. Last couple of weeks we've been working with energy, and energy has been scalar values, right? So the number of joules, kind of like some volume or some mass, right? Direction hasn't really been important, but now direction's back, and direction's going to matter. So momentum, lowercase p, is equal to, and all it is just mass times velocity. That's it. Notice I'm saying velocity, not speed, because direction matters. I haven't really been in the practice of putting vector arrows above variables, but this section I like to, so whatever. What is a unit of momentum? Unit. Like I know force is measured in newtons. I know energy is measured in joules. Each of those are composite units. This is going to be some form of composite unit. What is it? Okay. So mass is measured in kilograms. Velocity is measured in meters per second. Okay. Remember, if you ever forget units for something, and that would be helpful to know, maybe you're trying to interpret some graph or something. If you know some formula that's relevant, you can just do exactly what I just did here. Unit of momentum, mass is in kilograms, velocity is in meters per second. You can just reconstruct it, right? Okay. Now, does this have a name? As far as I know, it does not. It's just called kilogram meter per second, or unit of momentum. So it probably should have a name, but as far as I know, it doesn't. There is an alternate form for unit of momentum that sometimes you'll see though that starts from newtons. Now, you guys remember 1 Newton is 1 kilogram meter per second squared. That comes from Newton's second law of motion, F equals ma. So if you start from newtons, you'd have to multiply by what to get back to this? Seconds. Yeah, newtons times seconds. So Newton seconds. Okay. So you be ready to fill either one of these. The top one I tend to write usually myself. This bottom one you'll tend to see more often if there's a change in momentum. It's called an impulse, because that would involve a force for some time interval. So that's I think why that comes up. Okay, so that's what momentum is. That's what the units of it are. But how's that important or applicable to what we're doing, and how's that going to help us solve anything? Okay. Well, it turns out that momentum is conserved in a closed system, just like energy is. Except energy, remember, was a scalar value, so we weren't caring about directions, but now we're also caring about directions. So here, I can say something like this. The sum of momentum initial in a system is equal to the sum of momentum final in the system. That looks a lot like energy conservation, doesn't it? Except it's a vector quantity called momentum, mass times velocity. Okay. And something else too is gonna leave a little space here. Okay. Oh, okay. What particular application is all this momentum conservation stuff good for? Because some things that you guys have seen in this class is that a lot of times there's multiple approaches to things. Like, well, I could use say a car braking to a stop. What's the braking distance? You could go with the dynamic followed by kinematic approach and get some stopping distance, or you could do conservation of energy and solve it a little bit faster. Okay? Now, momentum conservation is actually good for a particular scenario that other methods just aren't good at solving, okay? And that's collisions. So useful for solving collision problems. So when I say sum of momentum initial equals sum of momentum final, that initial and final conditions are actually referring to pre-collision and post-collision. Okay? So before two objects collided, after two objects collided, if you add up all the momentum bits, it has to exactly equate. Is that right so far? All right, let's dive into an example. And as I go along the notes, I'm going to sort of be following this page. Right? So let's pick up starting with number 3, though. Okay? So two objects of some masses collide head-on, resulting in some measurements. Right? So you knew each mass, you knew each starting velocity, and you know one of the rebound velocities, something like that. Okay? So we're going to reconstruct this here. Okay. So let's look at just very basically some general collision. Remember, from now on, like starting today, whenever you see objects collide, think momentum conservation, something related to that. Let's just keep this to one dimension. Now, everything I teach guys next few days, you can expand to 2 and 3 dimensions, bring in vectors and stuff, but we're just going to stick to 1 dimension for today and for now. Let's say you got some mass A and some mass B. And let's get an axis that they're constrained along. So they're both just moving along this axis. Right? And give you guys a velocity A initial and some velocity B initial. Right? So they're headed straight towards each other. That's what I was trying to do. Straight at each other, right? Head-on collision. And then they're going to collide, and something's going to happen. They'll probably rebound off each other, right? I think, maybe? Let's assume they do. Because you might be thinking to yourself, well, hold on, man, what if they stuck together? But I'll talk about that in a minute. That would be possible. Let's say just a general case, let's say they rebound off each other, and how would they rebound off each other? Well, there'd be some VA final, and there'd be some VB final. Like that? Okay, so you guys can see how this is gonna be able to feed into something like this, right? If I add up all the momentum bits, just mass times velocity, before and after the collision, it has to equate, right? Because momentum is conserved. Okay? So let's do that. Say sum of momentum before the collision is equal to sum of momentum after the collision. Okay? Well, it's going to go like this. MAVA initial plus MBVB initial is equal to MAVA final plus MBVB final. Okay? Is that right? I have not given you guys any numbers yet, so let's throw some numbers in here and just play around with it, see what happens. I drew MA a little bit bigger, so calls 3 kilograms versus 2 kilograms. Right? So, well, that's what's true before and after. Right? Let's plug that stuff in. Right? So 3 kg, it's going to go there. And also over here, 2 kg is gonna fit right there and right there. I need to tell you something about velocities. So let's say the initial velocity for object A was 10 meters per second to the right, and I'll have object B going at 15 to the left. So let's call it negative 15, right? Mathematically, because 15 to the left. So I have positive 10 meters per second. I got negative 15 meters per second. And then, okay, so this is the structure of this is coming together, right? Okay, so. Okay. You guys good so far? All right, so what I've given you is the mass of each object, how fast each was going towards each other, and also that they're locked into just one-dimensional axis. Okay? And the question is, well, how do they rebound off each other? Now, here's where, hopefully you've caught on to this so far, but if you hadn't yet, then just by looking at the algebra of this, you guys see that there are two unknown values. Guys, can you solve one equation with two unknowns? No. This probably has many, many possible solutions, doesn't it? So I have to tell you something else. And this goes back to maybe like how these are rebounding off each other. Well, maybe that's some material property, kind of like coefficient of friction is a material property, right? I wonder if there's some coefficient that might involve like bounciness, maybe called coefficient of restitution. So maybe these things do collide and stick together. That would be like one extreme boundary condition. The name for that, by the way, is called perfectly inelastic, and we'll get to that by the end of class today. The other extreme condition is like perfectly bouncy, which is pretty close to Newton's cradle situation. I mean, that's probably about as bouncy as we could get, right? Okay. And what is this for this general collision? Well, it could be either of those, or maybe it's like two half-deflated tennis balls. They're like, just like bounce off each other, but not very well. Right? I mean, any of those could be possible. So I'm going to make up a number for one of these. Let's say VAF is, okay. Hey, could I write the little thought experiment? Does this sound right? Could I make up any number? Could I say like negative 1,000,000 meters per second? Would that be okay? Negative 1,000,000? There would be something wrong with that, wouldn't there? Okay, so that probably violates something. Do you think that would violate conservation of energy? Do you think if you did start doing energy accounting, like 1/2 mv squared, that if I did negative 1,000,000 meters per second, that would probably violate that, wouldn't it? Okay. So I can't quite make up anything, but maybe something like this. I'll call this negative 6 meters per second. Okay, so now this actually is solvable, isn't it? Okay, BDF. Okay, we're gonna figure out. See, once I've told you the rebound velocity of one of these, now it is locked in place, determinable exactly what the other has to be. Right, you guys see that? All right, so, guys, how much momentum was in the system to start with? What is 30 units of momentum, 3 times 10, minus 2 times 15 units of momentum? How much does that come out to? 0. So, wait, what is that? There's 0 momentum in the system. I thought these were each had a mass on the move. Yeah, but also remember that momentum is a vector quantity. Energy last week was not, but momentum is. So now it doesn't always have 0. Obviously, I just made up numbers that did. Okay. But that would be true that this has to 0 out. So this is negative 18 units of momentum plus 2 kilograms times VDF. You guys see if you add the 18 over and divide by 2, so VDF is going to be 18 units of momentum divided by 2 kilograms. VDF is positive 9 meters per second. Okay. Is that right? All right, so this must be equal to 9 meters per second because solve for it. Okay. I'll get some more. But of course, if I change this initial object A rebound speed to something else, then that would affect object B. Okay. Okay. Let's think about those different kinds of collisions that I made reference to, right? So you could have 2 objects collide and stick, 2 objects bounce off each other really well, or maybe something in the middle. Okay. And I said that even how much you can rebound off each other was probably constrained by like energy conservation. Let's do energy accounting. What kind of energy did those objects have? Well, it must have been kinetic energy, right? They weren't changing height, there was no springs, so maybe something to do with 1/2 mv squared. Okay. So 1/2 mass A VA squared plus 1/2 MB VB squared, well, initial, okay, initial condition. Okay. So here, what were these numbers? It was, let's do this on my calculator screen. 1/2 times 3 kilograms times 10 meters per second, and then square that, that's speed, plus 1/2 times 2 kilograms times 15 meters per second being squared. Now, it's negative, but negative squared just goes away anyway. Guess it's going to be 375 joules of energy. Okay, 375 joules. Is that? What about after this collision? Kinetic energy final. Well, we've got a new value. So I've got 1/2 times m times. Now remember, its rebound speed was 6 meters per second, so 6 squared, plus 1/2 times 2 kilograms times. And this came out to be 9, and then square that. Okay, that is 135. 135 joules. Huh. Do you guys see that the final kinetic energy is less than the initial kinetic energy? You guys see that? Well, hang on. I thought, didn't we just spend like 2 weeks saying that energy is conserved? And what, now it's not? Okay. Now, that energy doesn't disappear. So here's the detail. Right? During, I'm going to say non-elastic collisions, which is pretty much all collisions. But if AP ever uses the word elastic, then have this mental model in mind. Right, so anything except for that. Right. So pretty much anything else. Right. Some kinetic, well, I'll say some mechanical energy. But really, it's kinetic energy. Right. Is converted into other forms that we just don't have a really good way of accounting for in this class. So, for example, heat, sound, permanent deformation. Permanent deformation is a pretty big one, right? So, for example, if this was like 2 balls of clay smashing against each other, this would be permanently deformed, right? Force times distance, right? Or what about this? What if you fire a bullet into a block of wood? Do you think that bullet has to like push those wood fibers out of the way to embed itself in that block of wood, right? Yeah, so that would, okay, so now I'm starting to see why if you were to approach a collision problem from an energy conservation point of view, that would be really messy and probably not give you very good results, right? Yeah.
Is it possible to calculate how much energy went into heat, sound, and permanent deformation?
Could you calculate it? Yeah, in fact, you could do it right here. So wouldn't it just be the difference between these two? So in this example, this collision example, what's the difference between 375 and 135? I could say 240 joules. 240 joules went into, I'll say, non-mechanical forms of energy. Okay. Which might be deformation, might be heat, right? You measure the temperatures, these things, like that. Right? Okay, so this is why energy conservation is not good for solving collision problems. If you ever want to solve a collision problem, always do conservation of momentum, okay? And then go back and take a look at you can figure out like a change in kinetic energy, something like that. Okay. Now there could be a case where final kinetic energy, like post-collision, could be initial kinetic energy, say pre-collision. Okay. So I'm going to go back and modify this. See where I said final is less than initial. Right? If I want to make this universally true, I'm going to change this inequality to less than or equal to. Right? Because if you have something like this, then this is perfectly elastic. That's to say, like perfectly bouncy. Right? Like if you had the world's bounciest bouncy ball, and you drop it on the floor, this one boing, 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 boing. And just like for thousands of years, just like bounce on the floor. Boing, boing. You just kept doing that. Having something like that. All right. Guys good? All right. Next page in the notes. Let's do number 4 from this page. Now, what we're about to do is not really anything new. It's just sort of well, I just want to plant an idea with this, which is you got two masses. I give you a bunch of post-collision information, and then a little bit of pre-collision information. Say like, what was going on before the collision? So we'll just run this one pretty fast. Okay, number 4. In fact, I'm going to use the exact same numbers that I just used. So mass A is 3 kg, mass B is 2 kg, and I'll have VA naught as 10 meters per second. But what if you didn't know what VB naught was? But you did know after the collision. So collision that VA final was -6 meters per second, and the B final was +9 meters per second. Oops, make that a little longer. Do something like that. Okay. What if you have this? All right, so this is the same problem as we just did. That's why I'm doing this a little bit fast. All right, but sum of momentum before is equal to sum of momentum after. Then MAVA naught plus MBVB naught equals MAVAF plus MBVBF. You plug everything in, we got 3 kilograms at 10 meters per second plus 2 kilograms at some, well, we're going to pretend we don't know what VBO is, but just turn notes back a couple pages and you can obviously see the answer. Okay. 3 kilograms rebounding at -6 meters per second plus 2 kilograms rebounding at +9 meters per second. Okay. Now this time, what is the sum of momentum units post-collision? Also 0, right? -18 plus +18 is just 0 kilogram meter per second, or 0 Newton seconds. Okay. So then if you solve for this VB initial, it's just got to come out to 15 to the left, right? So -15 meters per second. Right? Right. So the reason they're going through that is I want you guys to recognize that one possible application of all this stuff is, say you're a forensic investigator trying to figure out what happened with a car crash. Right? Now, you would probably have, what would be more attainable would be the post-crash information. You could look at the streaks of, like the tire streaks on the road. You could figure out sort of like, okay, well, after these cars collided, they were going this fast. Here's the mass of each car. But what you really want to know is what happened before the collision. And this is sort of that thought process, isn't it? Something like that. What happened before the collision? Okay. But that's all, right. Otherwise, that's not really super new stuff. All right, but let's modify this a bit and say, hey, what if 2 objects collided and stuck together? Now, there's a name for that in physics. It's called perfectly inelastic. Or sometimes AP, your materials, they just say inelastic. Collision. And so inelastic. Right? Now, this is one of these boundary conditions. Right? So this would be one extreme possibility of a collision. So collide and stick together. And if they collide and stick together, doesn't that mean that they have the same final velocity? Right, same final velocity? Okay. So let's go back to the same masses moving at the same initial velocities. So the 3 kilogram mass A and the 2 kilogram mass B. But we're going to make a change. Right? This time they're going to be made out of, let's say, like wet clay. So they're going to collide and just go stick together. Otherwise, I'm going to give them the same initial velocity. So VA naught, I'll call 10 meters per second, just like before. And VB naught, I'll call -15 meters per second, also just like before. Okay. We'll do sum of momentum initial is equal to sum of momentum final. Okay. Okay. And this will start out the same way as before. So mass A, velocity A initial, plus mass B, velocity B initial. Okay, so far everything looks the same. Okay, but here's where things take a turn. Okay. And if they collide and stick, I could do the general setup, MAVAF plus MVVBF, but since they have the same speed or same velocity anyway, I could just factor that out. Okay. Or you could just skip to the next step and say, well, they're just going to make one giant mass, effectively, moving at some common final velocity. Solve for it that way. That's if they collide and stick. Is that? I'll tell you guys what too. The opposite of perfectly inelastic, collide stick, would be perfectly elastic. It's kind of like Newton's cradle, like perfectly bouncy. AP tends a lot more often to ask questions about this one we're doing right now, inelastic. And I'll tell you guys why. Because this setup right here is mathematically pretty straightforward. When we get to elastic, like bouncy, the math gets really crazy, but that's okay. I'll show you guys how to handle that tomorrow. Okay? But let's plug in some numbers. So we've got 3 kg moving at 10 meters per second, plus 2 kg moving at negative 15 meters per second, is all a collection of 5 kilograms, right? 3 plus 2 kilograms, moving how fast? Oh, well, you might remember from a few minutes ago, what was the total momentum in the system? 0. Because remember, it's a vector quantity, so it can subtract from each other. That's okay. So 0 total momentum acting on 5 kilograms? Well, so what is VF? Would be 0. Okay, so now, again, this is not universally true. It's just for the numbers I made up for this example. But yeah, got these 2 balls of clay. Got a big one moving slow and a small one moving fast towards each other. Couldn't happen. They could just like collide and dead stop. Just stop right there. So, come on. And do you guys remember we ran the kinetic energy numbers on this before? Let me dig up those notes. Here it is. Okay. Got 375 joules before the collision. So that would be true here also too, because I'm just using the same numbers. Okay. What is the kinetic energy final for this scenario? What is it? What is 1/2 mv squared with a v of 0? 0 joules. Guys see 0 joules? Okay. Now, before it looked like 240 joules went into non-mechanical energy, but for this perfect, that was when they partly rebounded off each other, like half-deflated tennis balls. But now for these balls of clay, looks like all of the energy went into non-mechanical, so probably all into deformation. So, right? This is an even greater change. Okay. All right, guys, right there. 4, 5. All right. Now let's look at number 6 on this page. Oh, sorry, this is the that's your page 2, but I get in touch with this. 1 second. Okay, so number 6 says a grenade flying through the air at given velocity explodes into 2 parts that travel along the same direction, like same axis of motion, okay? As which the grenade was originally traveling. At what velocity is piece B of the grenade traveling? And then a hint in parentheses here: applied perfectly inelastic collision, but in reverse. What's that about? Hey, I'm talking about a grenade exploding, and all day today I've been talking about like, oh, this stuff is really good for solving collisions. Like, what does one have to do with the other? How's a collision like an explosion? Well, let's draw this out and then make some connections, and you guys will see why. So number 6 on that page. So you got a some grenade, and it's moving at some initial velocity. Say v naught is, now the numbers I'm going to make up, probably not realistic at all for a grenade, but let's just run with it. Okay. So let's say like 15 meters per second. I don't know. And it's all one solid mass, but then it's going to pow, like explode into 2 parts. I'll call it mass B and mass A, like that. Okay. Let's say that mass B is 0.6 kilograms and mass A is 0.4 kilograms. Right. So that the initial grenade was just 1 kilogram. So here's your initial grenade right here. You're gonna take your heaviest lab weight, like chuck this across the field, like that. Right? And this thing explodes into 2 parts. Now, just to simplify this a little bit, let's just keep this all on the same axis of motion. Let's say like this dashed line right here. Okay. Now, of course, realistically, it's going to like a projectile parabola type path, but let's just focus on that. This thing is going to got a before and after photo. So here's before, right? And after the explosion, you got a pow, break into these 2 bits, mass B, mass A. Right? Then you gotta take off at different velocities. So throw a little explosion right here, like pow, like that, right? Okay. I'm gonna call this VA final, and then, well, no, piece B. Do you think it's possible that piece B, this explosion is so much that piece B actually gets kicked backward? That's probably actually what happened, right? Or maybe it's still moving to the right, but if it's moving to the right, would it be moving really slow? VB final? It'd have to be going slower than the original number, right? I mean, for momentum to be conserved, then this initial velocity, if these 2 like bust apart and one piece takes off faster than that, does the other piece have to go slower than that? Kind of makes sense? See, like the big picture of it. Okay. Now, I've left off a critical piece of information. You need to actually solve this, but I'll go back and fill in that detail later. Okay, let's set this up and start to solve it and see if we can make sense of this. The sum of momentum before the explosion is equal to the sum of momentum after the explosion. Okay. Okay. So, what does an explosion have to do with a collision? I haven't even answered that yet, but just start over and set down. So this grenade was initially 1 giant mass. You can think of it like putting the 2 parts together, give it some initial velocity. Okay. Isn't that the initial momentum of the system? That looks like 15 units, doesn't it? 1 kilogram, 15 meters per second, like 15 kilogram meter per second. Okay. And then after the explosion, where's all that momentum go? Well, some of it's going to go mass A, velocity A final. And some of it's going to go mass B, velocity B final. That's where momentum is. Right? Oh, you know what? This sure does look a lot like this from before, doesn't it? 2 separate objects come together, stick together. This is one object splits apart into 2 pieces, doesn't it? Hey, if you filmed this whole thing happening, like this grenade exploding, and then you ran that film in reverse, wouldn't it look like 2 pieces come together, colliding like perfectly inelastically? Yeah, that's what the physics of this is. This is a perfectly inelastic collision in reverse. That's what it is. And but you know what else? Hold on to this idea too. If that's also true, you guys remember how 2 objects colliding and sticking together, there was a huge loss in kinetic energy? Now, remember, that energy didn't disappear from the universe. It just went into like deformation and heat and sound, right? But mechanical energy, kinetic energy did decrease. Do you think if you ran this in reverse, that's to say like a grenade exploding, that would be more kinetic energy in the system post-explosion compared to pre-explosion? That would make sense, wouldn't it? But hold on a minute. If energy is conserved, where did that energy come from? It came from the explosion. Yeah, from that chemical reaction. There was some chemical reaction. Right? There was energy stored in those chemical bonds, and however you make a grenade explode. Yeah, that's where the energy came from. Okay, so I see this all coming together. This is just an inelastic collision in reverse. Let's throw some numbers in here. I know that this whole thing was 1 kilogram, because 0.6 plus 0.4 kilograms. Moving at 15 meters per second, so got 15 units of momentum. Okay. Mass A was 0.4 kg, moving so fast. Mass B was 0.6 kg, moving so fast. Okay. Let's say we're solving for VB final, like that. Okay. You see, we're running into the situation we ran into before, where I didn't give you enough information. You'd have to know one more thing, which would be somehow related to this explosion. You have to know the final velocity of one of these pieces. So I'll give you one of them. Let's call this number right here, VA final, 20 meters per second. That's going to go in right here, 20 meters per second. Okay, okay, now we can solve for VBF. Okay. In fact, let's play around this sort of as a variable before. I know I just gave you guys a number, but what if you made this like 200 meters per second? What do you think would happen to VB? Do you think it'd probably get kicked backwards even? Probably would. Right? What if you made VA final 15 meters per second? Just 15. What would mass B do? It would also be 15, wouldn't it? Because it looks like, oh, there was never an explosion at all. It was just like a dud, right? Okay. So do this. I got 15 kilogram meter per second, going to 8 kilogram meter per second, plus 0.6 kilograms VB final, like that. Okay. All right, so subtract the 8 over. So VB final is 15 minus 8, that leaves you 7 kilogram meter per second. Divide by 0.6 kilograms. Okay. And you should get 11.7 meters per second for VB final. That's good. Take a note down here. I'm going to say initial kinetic energy is less than final kinetic energy, and that the extra energy comes from a chemical reaction. Inside the grenade. Right? Yeah, so that's just an inelastic collision in reverse. Right. Right. And you know what? A grenade exploding and therefore one mass breaking into two smaller masses, they each are moving independently, and also the kinetic energy of the system increasing as a result. You know what this reminds me of? This reminds me of throwing a baseball on a frictionless baseball field, right? Because you could be, say, the pitcher and the baseball. It could be two separate masses that were just initially together. And then they separate apart and do their own separate thing. Right? If you know the final speed of one, you could figure out the final speed of the other if you know their masses. Right? Guess that? Right. So that's the next place we're going with the story. Then we'll talk about perfectly elastic collision, which is like perfectly balancing, the opposite of this. And then we'll talk about coefficient of restitution, which is a way to quantify bounciness. Okay? And finally, impulse. Right? So that's next few steps of this adventure.